Okay, Integrated Math 1 fans, our topic for today, this is Notes 1-2, Modeling Quantities. So we're going to be looking at ratios and proportion in this lesson. So before we start though, let me give you your joke of the day. Did you hear the rumor about the butter? Well, I'm not going to spread it. So our goal for today, our objectives are to set up ratios and proportions to solve problems and solve proportion problems. Okay, so kind of the same thing there. So we're going to start with what we call a rate of change problem. And in this example number 1, Mr. Covell is driving 60 miles per hour. Fill in the missing values in the table and graph the relation on the coordinate plane. So we have this table here, and we've got the time in hours. That's going to be our x variable. And then the distance in miles is going to be our y variable. And then on the right of this, we see a coordinate plane here. So if he's traveling 60 miles per hour, if that's how fast he's driving, so this is really telling us our speed or our velocity for that. If he drives 0 hours, that means he hasn't gone for any amount of time, then he's driven 0 miles. If he has gone for 1 hour, he goes 60 miles per hour. So 1 hour would be 60 miles. That would be his distance. Now notice that we skipped from 1 to 3 in the time. So we didn't put 2 hours here, but every hour he's going to travel 60 miles more. So if we go to a second hour, if I put a 2 here, if he travels 60 more miles, that would put us at 120, 60 plus 60, or 60 times 2. 3 hours, each hour he travels 60 miles. 3 times 60 is 180. And then in the last part of the table here, they tell us the distance, the y value, and they're asking for the x value. So if he drives 360 miles, can you think of the number of hours that would be? Well, instead of multiplying by 60, if we're going from the y variable back to the x, we would divide, and this would be 6 hours. And then what we can do here is go over to the coordinate plane. Now notice I've already numbered this. I've already labeled my plane. It's up to you how you choose to label. I counted 2 spaces on the x-axis because if I went further than that, if I did 3 spaces, I'd actually run off. And then going up, I counted 3 spaces. But it's up to you how you want to space that out. The key thing is that I space each axis the same way. And I also want to label what each axis represents. So my x-axis, this is our x, that's going to be the time in hours. That's our measurement. And then the y-axis, going up, is going to be the distance in miles. Okay, so we're going to plot the points, x comma y. 0, 0 is at the origin, right there. We have 1 comma 60. And then we have, now I'm going to skip 2. We'll do 3 and 180. And then 6 and 360. Now I'm not going to connect this. I'm not drawing the line here. These are 4 specific values. That's all I'm going to plot, 4 points. But one thing that's kind of interesting is notice that they all seem to be on a line. I could connect these, and by drawing one line, I would be able to connect all 4 points. So that's kind of interesting for that. Now, a couple things in terms of vocabulary, we're going to make a few connections here. The rate of change, they actually told us that at the beginning. It was 60 miles for every 1 hour. Now I'm writing that as a fraction, 60 over 1. And if we look at that, the rate of change, so we go 60 miles for every hour. If I think of this on the graph, if we count the slope, the rise over the run, it's always going to be 60 and 1. Okay, we rise, that's the ratio, plus 60, and then we go over positive 1 space. If I go from here to here, I would rise. Now this would go up 120. This change, the rate of change, my distance would be 120, but the number of hours would be 2. But notice that if I look at 120 and 2 as a fraction, I still get 60. And if I go from 3 to 6, my y value, my distance, the change is 180. And I'm going up, so it's positive. And then if I go over 1, 2, 3 hours, but notice that 180 over 3, that rate of change is also 60. So what happens here, and I could have done this actually just looking at my values. If I take the y divided by the x, we have 60 over 1. We have 180 over 3, we have 360 over 6. And all of these are equal to the same value, which is 60. So graphically, in terms of a visual here, we're talking about slope. The rate of change is the slope of this linear relationship. Okay, so this would be a line. But if we're just looking at the values here, we would say that each of these fractions is proportional. And another word for fraction is ratio. Okay, so let's look at a couple definitions here. The concept of a ratio, it is a comparison of two numbers by division. So if I write the word fraction on the side here, notice that the word ratio is actually inside of it. So a ratio is just a fraction, and fractions we typically look at with division. Now we could write this, let's say we had 2 over 3. We could also write the ratio as 2:3. So sometimes you'll see it this way. Most of the time we write it as a fraction, like this. Now a proportion is two ratios that are set equal to each other. So if we say that ratios are proportional, that means that they're all equal to the same value when we simplify the fractions. One way to test that, actually, so if we have two fractions, two ratios equal, we can look at what we call the cross products, A times D and B times C. We call those cross products. If they are equal to each other, then that means that the ratios are equal. That's what it means to be proportional. So if I use, for example, 2 over 3 and 4 over 6, and the question, are those equal to each other? Well, we can take 2 times 6 and look at that. We get 12. We can take 3 times 4 and look at that, and we also get 12. If the cross products are equal, then these two ratios are proportional. Now you may look at that and say, well, wait a minute. If I take 4 over 6, that fraction, I can reduce it, I can divide it, in this case by 2, and I get 2/3. Can't I just check that these are the same by doing it like this? Yes, you can. Another way that you can do it, if you wanted to take a calculator and take 2 divided by 3 and get a decimal value, 0.6 repeating, or you could take 4 divided by 6 and check and see, hey, those are the same thing. So again, I can test this a bunch of different ways. All right, so let's look at some examples here. Directions solve the following proportions. Okay, so the second example here, we have 3 over 7 equals something over 21. Now the process we typically use is called cross multiplying. When we solve a proportion, what we do is we take the cross products. Now what I'm going to do, sometimes I've seen people draw lines between them. That's kind of what I did here. I'm actually going to circle that cross product. Now that is 7 times x. So 7x equals, 7 times 7 is 21. 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 The other cross product is 3 times 21. Now normally I'm not going to write this down. I'm actually going to do the multiplication in my head and say that's 63. And what we have here is an equation. Remember, a proportion, all it is an equation. Okay, so when I do the cross products, when I cross multiply, I still need the equal sign here because I am solving this. And now this is 7 times x. To undo multiplication, I can divide by 7 and we get 1x equals 9. Now there's the answer. The question is that correct? Well, if I'm just going to take the fractions here, 3 divided by 7, there's a decimal. And then instead of x, if I replace that with 9 and type 9 divided by 21, do we get the same decimal? Yes. So this is the value of the left and the right sides. If they are the same, then that means our answer is correct. Now again, you may look at this and say, wait a minute, I actually could do that in my head because I was looking and I noticed that to get from 7 to 21 here, I could times by 3. And if I took 3 and I did the same thing, 3 times 3 is 9. So there are some patterns and shortcuts that you can sometimes use when you are solving a proportion. So for example, in number 3 here, if we try to do that, to get from 11 to 44, we would multiply by 4. So because these are proportional, I would have to multiply the same way. So something times 4 would give us 16. So actually in this case, maybe we want to go from the right to the left. To go from 44 to 11, we would divide by 4. To go from 16 to a, we would divide by 4. And we get a is equal to 4. So sometimes you can do that. If we cross multiply, which is always going to work, we would have 44 times a equals, and then 16 times 11 is 176, and then we divide, and a is 4. And then again, we would want to check our solution. So if I go back to the problem here, 4 divided by 11, okay, is this value 0.36 repeating. 16 divided by 44, is it the same? Yes. So this is correct. Now, number 4, again, you can say, hey, there's a pattern to get from 7 to 14. In this case, because this is x plus 2, I'm going to just cross multiply. You'll notice that sometimes I circle the diagonal, the cross product that has the variable. That's how I always start it. So now this is, you got to be careful here. This is 7 times this whole denominator. So I'm going to write that in parentheses, equals, and then 3 times 14 is 42. So to solve this, the first thing I need to do is simplify the left side. I'm going to distribute the 7. So 7x plus 14, because that's 7 times 2 is 42. Now to move the constant, I'm going to subtract it. So we get 7x, that's just 0, equals 28. And now to undo the multiplication, we divide by 7, and we get x is equal to 4. Okay, so again, we have 4. The left side, 7 divided by 3 is 2.3, repeating. Now the right side is 14 divided by x plus 2. So if I take the 4 and I substitute, I get 4 plus 2, so I'm dividing by 6. Same thing. And that is the end of part 1 of the notes.